Okay, except for one more quick add-on section, this is the culmination of our polynomial functions, because today we're going to learn how to find the zeros of polynomial functions and graph correctly from there. It's a pretty long section, so it'll be a pretty long video. First of all, Descartes' rule of signs says that if you've got f of x, the number of positive real zeros is the same as the number of sign changes, or less than the number of sign changes by a positive even integer. So let's say you've got 5 sign changes. Then there's either 5 positive real zeros or less than 5 by an even number, so it would have to be 4. If there were 4 sign changes, then there would be either 4 positive real zeros or less than that by even, so down to 2. The number of negative real zeros, you'll take f of negative x and find that. And then it's the same idea. The number of negative real zeros will be the sign changes of f of negative x, or that number by a positive even number. So example 1 says, determine the number of positive and negative real zeros of f of x. So what do I mean by sign changes? You have a positive to a negative here. So we've got positive, negative, positive, negative, positive. How many sign changes are there then? 1, 2, so positive to negative, negative to positive, positive to negative, negative to positive. There's 4 sign changes. So that means that there are 4 or less than that by an even number, so 2 positive real zeros. To find the negative real zeros, we plug in f of negative x. So everywhere where there is an x, we plug in negative x. Negative x to the 4th is positive x to the 4th. Negative x cubed is negative x cubed times negative 14 is positive 14x cubed. Negative x squared is positive x squared times 71 is positive 71x squared. Negative x times negative 154 is positive 154x plus 120. So our signs are positive, 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 positive. There are no sign changes. That means, what did it say? If f of x has only one variation in sign, then there is one negative real zero. But if it has no variation in sign, then there are no negative real zeros. Next, This is a biggie. The rational zero theorem. If you have a polynomial and you say that P is the factors of the constant, so A naught is P, and Q is the factor of the leading coefficient, then P over Q in lowest term is a rational zero if P over Q in lowest terms is a rational zero of F, then P must be a factor of F and Q must be a factor of A sub n. So basically, well, let's just look at an example. So, if we look at negative 12, P is going to be the factors of negative 12. What will go into negative 12 evenly? Well, positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 4. 5 won't, 6 will, 7, 8, 9, 10, 11, 12 will. Then R are the factors of 3. So positive and negative 1 and positive, negative, and 3. So the potential rational zeros of f of x are this. It's each P over each R. So first you have all these over 1. So it's just plus minus 1 because it's over 1. Plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 12. Then next we take each of the P and put it over 3. So we'll have positive or negative 1 over 3. Positive or negative 2 over 3. Positive or negative 3 over 3 just gives us 1, which we already had, so we don't need to mess with that. Then positive or negative 4 over 3. Next will be positive or negative 6 over 3, which is 2, which we already have, so we don't need to mess with that. And then we'll have positive or negative 12 over 3, which is 4, so we don't need to list that. These are therefore the potential rational zeros of f of x. What do I mean by potential? Not all of them will be zeros, but these are the ones that are possibly zeros, not any others. So 5 would not be a zero of f of x. So we aren't able to limit it down to just a few, but a lot less than trying every single number going out to infinity. So what we're going to look at is finding the real zeros of a polynomial function. To do that, we have to list the potential real zeros. Now, for example 3, we've already listed them, so I'm not going to go through and do that again. Just going to copy it over. So here's how it goes. Once we have the potential real zeros, we start testing them. And we test them either with synthetic division, or we can test them by plugging in the number. So whichever is easier for you. I'm going to test by plugging in. So we start with -1. We just start with the very first one. And we're going to plug in -1 for x into our function. That gives us 0. That's good. That means that we've already found one. That means that x equals -1 is a 0 of f of x. And so x plus 1 is a factor of f of x. That's a good thing. So we can already start writing f of x with x plus 1. Okay? So now we need to find another factor. We do that by using synthetic division. So since -1 was a factor, or was a 0, we're going to put that in the box and our coefficients, and then we're going to perform synthetic division. So bring down the 3. We've already done a section on this, so I'm not going to go through this one at a time again. If you don't remember synthetic division, you can go back to that previous section. But here we go. So that means that the another part here is 3x squared plus 5x minus 12. Okay? Well, now we need to factor that. So, taking 3x squared plus 5x minus 12 to factor, 3 times -12 is -36. What multiplies to give us -36? That adds to give us positive 5x, 9, and -4. So I'm factoring by grouping here. Which we also reviewed in the last section. And you should know how to factor by now anyway. So I'm not going to focus on that. I'm just focusing on the new stuff. Okay. So what this means for us is that f of x factors to be x plus 1 and then x plus 3 times 3x minus 4. So we've completely factored. Now it wants us to find the real zeros. So at this point, we just set each of those equal to 0. So x is -1, x is -3, and x is positive 4/3. So our real zeros are -3, -1, and 4/3. Look at another example. So, find the real zeros of this function. So we need to start with our p's over q's. So the factors of p are that's 9, by the way, plus or minus 1, plus or minus 3, plus or minus 9. And then Q, which is 2, the factors of 2, plus or minus 1, plus or minus 2. So P over Q are our potential real zeros, and we do every combination there. So starting with Q equals plus or minus 1, we've got just plus or minus 1, plus minus 3, plus minus 9, and then with plus or minus 2, we've got positive or negative 1 over 2, plus or minus 3 over 2, and plus or minus 9 over 2. So now we choose, starting with, let's just start with, I erased there, negative 1, and plug in. So we'll plug in negative 1 for x. I'm not going to write that out, but it is written out in your notes for you. And we get 0. So that means that negative 1, or x equals negative 1, is a 0 of f of x, and x plus 1 is a factor of f of x. So we do synthetic division. Let's write it down first, though. So f of x is, we know that x plus 1 is a factor, and now we're going to find the rest. So negative 1 in the box, coefficients out here, and I'm going to go through this synthetic division quickly. We've already talked about how to do it, so I'm not going to spend the time on it here. If you need to review, you can always go back to the previous section. And so in our second set of parentheses, we'll go, let's see, we started with a 4th power, so it's 2x to the 3rd plus 11x squared plus 18x plus 9. Now, so we've got this new factorization here, or this new polynomial basically, where x cubed is the degree, and we can't factor it easily. So what we do is the exact same thing all over again. So we try, let's see, negative 1 worked. Let's try 1. When you plug in 1, you get 40. So 40 is not a 0. So we can't, or 1 is not a 0, so we can't use it. So next is negative 3. Try f of negative 3. We get 0, which is good. We didn't have to go too far. So that means that x equals negative 3 is a 0 of f of x, and x plus 3 is a factor of f of x. So now we've got our x plus 1, and then we've got x plus 3. And then we've got something else that's going to go in here to give us the rest. So we do synthetic division again. So we'll take negative 3, and this time we use the coefficients of this. You may have to watch this video a few times, and we'll do another example. But we use the coefficients of our blue function there. You could probably use the original and be okay. But if I use this one, it's a little bit shorter. So I'm going to go through synthetic division here. Okay? And let me go back here and pick this up. So that means that now we've got 2x squared plus 5x plus 3 in here. And that can luckily be factored easily. So take 2x squared plus 5x plus 3 and factor it. So 2 times 3 is 6. What multiplies to give us 6? That adds to give us 5x, or 5. That'll be 2x and 3x in there. Out of the first pair, we'll pull out a 2x, left with x plus 1. Out of the second pair, pull out a 3, left with x plus 1. So it factors to be 2x plus 3 times x plus 1. So now, in place of the 2x squared plus 5x plus 3, we can put 2x plus 3 times x plus 1. And we have finally finished factoring f of x. Now that we've finished factoring it, we can find our zeros. So set each of them equal to 0, all 4 factors. Notice we've got an x plus 1 in there twice. So actually what we need to do is get rid of one of those. And to simplify this correctly, then we'd have x plus 1 to the second power, and then the rest of it. Because we don't need to have it written in there twice. I'm going to go back to solving for x. And so our zeros are -3, -3 halves, and -1. There will be more examples of that in the next section on complex zeros. But if you need to go back and just rewatch that video, that previous example, do that as much as you need until you grasp it. For example 5, we're going to write a polynomial of degree 3 that has the zeros 2, which have a multiplicity of 2, and -5. So our polynomial have the zeros 2. So if there's a 0 of 2, then that means that there's a factor of x minus 2. And it says it has a multiplicity of 2. So that means that the exponent there, the degree, is 2. And then it's got a 0 of -5. So the factor must be x plus 5. So a polynomial of the degree would be this multiplied out. So we'll say and FOIL. And distribute. And then when we simplify, we get x to the third plus x squared minus 16x plus 20. So this is one example of a polynomial that fits this description. Now, you could get a polynomial, any number you put in here. You could put a 2 in here and then multiply that through. Or you could put in a 3 or a 4 or whatever. Whatever number you want can go in there. Or you can just leave it as 1. But all of those would be any, where A is any number here, would be options for a polynomial that fit this description. And then we've got this theorem called the bounds on zero theorem. It says an upper number, m, is an upper bound to the zeros of a polynomial, and little m is a lower bound. So a 0 has to be between that upper bound and lower bound in certain cases. You can read through that. It'll be easier to explain looking at an example, I believe. So for this function, use the bound on zeros theorem to find the integer upper and lower bounds to f. So what we do is we start with our p over q's again. So p, negative 15, the factors are plus or minus 1, plus or minus 3, plus minus 5, plus minus 15. Q, the factors of 3 are plus minus 1, plus minus 3. So P over Q would be any of these options. And then all of those over 3, so plus or minus 1/3. 3 over 3 is 1, so we don't need to worry about that. Plus or minus 5/3. And 15 over 3 is 5, which we already have. Okay? So our theorem says that capital M greater than 0 is a real number, and if the third row in the process of synthetic division contains only numbers that are positive or 0, then M is an upper bound. So we're looking at a positive number where the third row are only positive. So the first positive number in our P over Q is 1. So we'll start with synthetic division with 1. Okay, now it said the third row has to be all positive. It's not. There's a negative 15 there. So that means that 1 is not an option for the upper bound. So we try the next positive number. The next positive number is 3. All the numbers in this third row are positive. So that means that our upper bound is 3. x equals 3 is the upper bound. Now we need to find the lower bound. So let's go back and read this. If you choose a negative number, I'm reading right here, by the way, and the third row in the process contains numbers that alternate between positive and negative, then m is a lower bound. So the first negative number was -1. So we try that. They do not alternate. We have positive, positive, negative, negative, or positive, negative, and then negative, negative. So they don't alternate. So -1 is not an option. The next negative number is -3. So we go through and try that. Okay, we are alternating here. We've got positive, negative, negative, positive, positive, negative. So that means that m is -3, or x equals -3 is the lower bound. So what did that tell us? That means that, looking back, there has to be a 0 between those two numbers. So a 0 of f of x exists between x equals 3 and x equals, well, that should be the other way around. Between x equals -3 and x equals 3. We'll look at some more examples with finding zeros in the next section, in the next video.